so I guess we'll get started on some of these number theory problems. And so we probably won't get to all the problems I sent out yesterday, but it would be nice to at least, get through a lot of them. So we'll probably start with the problems that I called problems, and then move on to some of the ones I called harder problems. So let's, I guess, get started with the ones I called problems. So I guess let's start with the first problem that I put on there, which was basically just how many ordered pairs comma n of positive integers satisfy m squared times n is 20 to the 21st power. And this is basically a problem from like one of the tests that led to the USAMO of last year in 2020, except I modified it a bit. But yeah, this is basically a problem from the AMY last year, pretty much. So what do people think the answer is? Just like put it in the chat, I guess. You can put it directly to me or in the public chat. Either is fine. So I'll give people another minute to like look at this, think of what they think the answer is, and then I'll show people how to do it. So, feel free to tell me what you think the answer is.
Answer says 11.
Okay, so I see some answers, but I think a lot of these answers are these answers that I've heard, they're all actually, so someone suggested 21, someone suggested 11, someone suggested 1. But actually it turns out the actual answer will be bigger than all of those. And so for this problem, this is sort of similar to the first problem we did yesterday in that it's going to be important to look at the prime factorizations. So let's take this number 20 to the 21st power and write it in terms of its prime factorization. So 20 is 2 squared times 5. So this number is 2 squared times 5 to the 21st power. So it's 2 to the 42nd power times 5 to the 21st power. Okay, So now, like any prime number that divides m or n must divide this number. So they can be written as, so when you take m and n's prime factorization, you get like this, where possibly a or b or both could be 0, but these are not, a and b are non-negative integers. And similarly here, c and d are non-negative integers. We would allow them to possibly be 0. And so now let's see what this equation gives us. It's going to give us m squared times n is 2 to the 2a plus c times 5 to the 2b plus d. And so for this to happen, like, we're going to need the exponents of the 2's to match up and the exponents of the 5's to match up. Because by the fundamental theorem of arithmetic, whatever the prime factorization is, it's unique. And so these would both be prime factorizations, possibly, dropping some terms with exponent 0 or whatever. And so like somehow to make them match up, these are going to end up having to match up. And these are going to have to end up matching up. So we have 2a plus c is 42, and 2b plus d is 21. And now, how many possible values are there for a? Well, it can be anywhere, like 2 times a is at most 42. So a is at most 21, giving us 22 choices for a, anywhere from 0 to 21 for a. And then whenever we choose a, that'll determine c by just saying c is 42 minus 2a. And now 2b less than or equal to 21, since b is an integer, it has to be at most 10. And so there are 11 choices for b, anywhere from 0 to 10. And then d would be uniquely determined by that. And so there are 22 ways to choose a and c, 22 ways to choose a, and then that determines c. 11 ways to choose d and b, because there are 11 ways to choose b, and then that uniquely determines d. And so the number of ways to choose all of them in total is like the number of ways to choose a and c times the number of ways to choose b and d. The number of ways to do one thing times the number of ways to do the other thing is the number of ways to do them both you can think of. This is, a basic combinatorial, a basic vacuum combinatorics.
How did choosing A and B be 22 ways?
Oh, sorry. I mean, like choosing A and C is 22 ways because like there were 22 choices for A because it has to be somewhere from 0 to 21. And then whenever we choose A, because this is 22 choices, that'll immediately tell us what C is by this equation. And so there are 22 ways to choose A and C. And then there are 11 ways to choose B and D. So maybe I should write that down. And I should be clear what I mean. It's like that many ways to choose.
Cannot B and D be 0?
Yeah, we allow B and D to be 0, yes. So like if A were to be 21, then C would be 0, and we allow that, that's fine.
There is a lighting problem in upper left corner of the board.
Some
Some lighting problem in upper left corner, please.
I'll just put it below here. 22 ways to choose the ordered pair A, C. That's good. Okay, there. And so yeah, once we do this, the number of ways to combine them is just like the number of ways to choose this times the number of ways to choose that. Like you could imagine like a big table with the 8 possible choices for A and A, comma C written along the top and B, comma D along the side, and just like each possible choice gives you one choice. So the answer to the problem is 22 times 11, which is 242. And yeah, and this sort of relates to this basic combinatorial principle that like, if you want to do two things, the number of, and they're independent of each other, the number of ways to do it is the number of ways to do one thing times the number of ways to do the other. But I don't want to talk too much about combinatorics today in this lecture because, you know, this is a number theory lecture, not a combinatorics lecture. But yeah, that's this problem. Does anyone have any questions about this problem?
I guess we must proceed. Yes, there isn't any.
Instead of declaring 21 ways of finding A, why didn't we declare 42 ways of finding C?
Well, the thing is, like, we could once, like, if we're trying to choose A and C, because like they're dependent on each other. So like, if we're trying to choose A and C, they're not both independent. We sort of could say, we could sort of think of it as pick them in order. And so if we pick A first, there are 22 ways to do it, and then that determines C. If we wanted to pick C first, well, it would have to be between 0 and 42, but it wouldn't just be completely free choice, because you would have to make sure that it's even to make sure that A would be an integer. And then like, if you wanted to count how many even numbers there are between 0 and 42 inclusive, you could say, you know, 0 to 4 up to 42, and there are 22 of those. And so then like, you could say 22 ways to choose C, and then that'll uniquely determine A. So you could say like A is 21 minus C over 2. And so like, that could be another way of doing it. So, any other questions? If not, I guess I'll move on to the next problem.
So there must be 21. So how did we get 22? I have
Oh,
just a
that's
little.
because, oh yeah, that's just because like when we say 21, like there would be 21 of them from 1 to 21, and then also there's 0. So the extra 1 comes from the fact that we're including 0.
Let's move on.
Okay, let's move on. So yeah, hope that worked. And so let's move on to the next problem. So we're asked in this problem to find the largest, did I say, what did the problem say? Okay, find the largest positive integer n such that n plus 10 divides n cubed plus 100. So, what did people think the answer was to this problem? You can put it in the chat. Yes, someone says, oh, I guess I should maybe bring this a little more. Yes, someone says 890. Yes, I hear 890 from a couple people. Yes, that's correct. So I'll go over this maybe pretty fast and then maybe move on pretty fast. So yeah, basically this is another idea about the Euclidean algorithm that basically, if we take this n plus 10 divided into this n cubed plus 100, well, you can just sort of repeatedly get rid of this n cubed. Like you can repeatedly get rid of the high degrees and replace them with low degrees. And so you could say like, you know, n divides this, n divides this. And so it divides, you know, this minus that, or, it, you know, we can do it the other way. We can subtract it the other way and so say, now we have this, and then do it again because we know it divides this. So it divides this 100n plus 100, and then it divides 100n plus 1000, subtract again, and we get that n plus 10 divides 900. So n plus 10 is at most 900. And so n is at most 890. And then you can see that like if n is 890, like this will work. And then like you can just follow back through everything. Like we'll know this works. And so since this works, and then you know this works, so then this will work. And then you know this works, so this will work. So yeah, 890 is the largest possible, and it does in fact work. So that's the answer. And then there's an alternate way of doing this problem, which is more like you, instead of doing this sort of one step at a time, we can just sort of get rid of the n cubed all at once, which is that like, if you know the factorization of like sum of cubes, then you'll know that n cubed plus 10 cubed will be n plus 10 times n squared minus 10n plus 10 squared. And so we know that n, so then we can just say n plus 10 divides n cubed plus 10 cubed. And then just subtract those directly and say n plus 10 divides 900. In fact, this sort of relates to a fundamental fact about polynomials, which is like whenever you divide a polynomial p of x by x minus c, where c is a constant, the remainder you get is p of c. But again, I don't want to, you know, I don't want to talk too much about this sort of algebraic polynomial facts too much, because I do want to sort of focus on the topic of, you know, number theory somewhat. But yeah, this sort of does tell you that like there is a lot of connectivity between the different branches of math. But so yeah, but you can sort of think about this as a fact about polynomials related to it. But again, I don't want to get into that too much right now. But yeah, any questions, or I guess any questions? If not, we'll move on to the harder problems.
Can you please once again go through that step-by-step step-by-step solution that is given there?
Oh, right. So okay, if n works, we know this, then we also know this happens. Like we also know this happens no matter what, because this is n squared times n plus 10. So if we subtract these, we would have to have this. And then we could also, and so now we got rid of the n cubed, and now we're only down to a square. Now let's get rid of the square, because this multiplied by 10n. So then subtract these and get this. Now we're down to a linear term, get rid of it by multiplying this by 100, subtract again, and you get this. And so then n is at most 890, and then if n is 890, then this works, and this works, so then subtracting these, you get this works, so then subtracting these, you get this works, and then this works, subtract again, and you get this works. So like, you can just sort of, you can use it to go both ways, sort of. So 890 is the largest that could work, and it does, in fact, work. Does that help? Is that clear? So. Oh, and the thing someone put in the, yes, that is this sort of alternative way of doing that. Yes. So yeah, n plus 10 times n squared minus 10n plus 100. Yeah, that is definitely an easier way of just sort of, instead of getting rid of the cubic terms one step at a time, you just sort of get rid of it all at once. And so yeah, by that thing I said earlier, like if you write this as n minus negative 10, then the remainder of this polynomial on division by n minus negative 10 is what you get when you plug in negative 10. So that would be negative 10 cubed plus 100, negative 900. And so you could just sort of use that directly, this sort of polynomial fact, like the remainder theorem or whatever they call it. So yeah. And yeah, I think someone in the chat put this formula, but it was a bit off. It should be, n squared minus 10n plus 100. Just, to be aware of that. Yeah, so I guess if there are no other questions, I guess I'll move on to some of the harder problems. Okay. Yeah, let's see this m greater than or equal to 2 problem. And yeah, so these harder problems are more up to the actual level of like what you could reasonably see as like problem 1 or problem 4 on something like the IMO, for the most part. And some IMO 1 4-level problems are more difficult than others. These problems are not necessarily the most difficult 1-4s, but they are like, for the most part, 2 of that level of an IMO 1 or 4. So yeah, so let's see this problem about the positive integer n. So yes, someone says m greater than or equal to 2. So yes, that is actually, the answer, but I guess I shouldn't spoil it too fast before I, set the problem out loud. Basically, we have this sequence starting with A0 is, you have a positive integer m, and then you say A0 is m plus 1/2. And then a sub k plus 1 is a sub k times the floor of a sub k. And then the problem is find all positive integers m such that this sequence will contain at least one integer term. And so if we look at this, basically like if at any point you have some integer n, basically like if you have n plus 1/2, then the next term will be n times n plus 1/2. So if n is even, this would be an
Excuse me.
integer and we would just be done. Oh yes.
Someone in the chat is saying that they don't understand the question. Can you explain the question?
Oh,
And,
right, the floor
someone is
function.
saying
Yes, I
that,
should.
What is the meaning of this L type symbol?
Oh, right, yes. This floor function is that basically for any real number, the floor function, for any real number x, this symbol, the floor function of x, is the greatest integer that is at most x. So you have like this property. So for example, the floor of 8 would just be 8. The floor of the square root of 5, since the square root of 5 is between 2 and 3, the floor of the square root of 5 would be 2. The floor of 7 over 2 would be 3. The floor of pi would be 3. The floor of, negative 4.3 would be negative 5, So this is the floor function. Oh, I guess I should say that's what I need to say. So yeah, and it's always an integer. So yeah, that's the floor function. So yeah, if we have a term with a sequence that's of this form n plus 1/2 for some integer n, the next term would be n times n plus 1/2, because the floor of this would just be n. And so if n is even, this would just be an integer and we would be done. We would just say, okay, we won, we got an integer. And so n would work. If n is odd, then this would be an integer plus 1/2. It would be n squared plus n minus 1 over 2 plus 1/2. And so, either we get, if we start from a number that's an integer plus 1/2, we move to either an integer or an integer plus 1/2. So either the entire sequence is composed of numbers of the form an integer plus 1/2, or there's an integer at some point. If there's so we just need to rule out that latter case of when is the entire sequence an integer plus 1/2. And so let's look at this. How does this change from step to step? The only bad case is when n is odd. So let's look at the next step. What happens? When would this be odd? Well, if n is already odd, n squared would be odd. And so the bad case for this would be when n minus 1 over 2 would be even. And so the bad case would be, in these two steps, would be when n is odd and then n minus 1 over 2 is even, i.e. when n is 1 mod 4. And so maybe if you did another term, if you play around with this, it turns out to be useful to think of it instead of thinking of it as going from an odd number n to n squared plus n plus 1 over 2, it'll be more useful if you subtract 1, to think of it as going from n minus 1 to n squared minus 1 plus n plus 1 over 2. And this will now factor as n minus 1 times 2n plus 3 over 2. And now what does this mean? So it means that there's this relationship between if AK, basically it means that there's this relationship because we're always dividing by 2. So when we look at this relationship between the integer part of the term minus 1 and the integer part of the next term minus 1, there's this sort of relationship where we're multiply by some odd number, whatever this number is, it must be odd, and then divide by 2. Meaning, we're dividing by 2 at each step. So we lose a factor of 2 at every step. And so this can't keep going on indefinitely. It must stop at some point when we would eventually get some number n minus 1 that would be odd, when we've divided out by 2 as many times as the original n minus 1 has in it. And so we would eventually get to some number n minus 1 being odd, and then n would be even, and then the next term we would get an integer. That would have to happen when we would run out of factors in n minus 1, unless n is equal to 1. That's the thing. If m is greater than 1, then this is a positive integer, meaning it only has you can take its prime factorization, and there are at most finitely many 2's in it. And so eventually it will run out of 2's, and then you'll get to an integer. The numbers of this form, like the integer part minus 1, will run out of 2's, and then you'll get to an integer. But if m equals 1 to begin with, then what do we get for the sequence? 1 plus 1/2, and then the floor will just be 1, and so we'll just be multiplying by that. 1 plus 1/2, 1 plus 1/2, 1 plus 1/2, and so on. And the sequence consists only of this, and we never get an integer. So for m is greater than 1, we will always get some integer term. And then for n equals 1, we never get an integer term. So that's the answer. And then if you were on an actual Olympiad and you wanted to write this up, you could say something like, the answer is m is greater than 1. For m is equal to 1, we can see that it doesn't work by, explain this part. And then for m is greater than 1, suppose for the sake of contradiction that there are no integers, then, every term is an integer plus 1/2. And then you could explain something like, let, however you wanted to explain this, it could be nice to say, let, c sub k be a sub k minus 3/2, which would be the n, this n minus 1 part. And then you would say c sub k plus 1 is c sub k squared plus 5/2 times c sub k. You could get, because it's 2 times n plus 1, n minus 1 times 5 is this one. And then explain how this would mean that since c0 is some positive integer, and then the exponent of 2 in the factorization decreases every time, that you would have to get to a contradiction. And then you would be done. And so yeah, this problem is IMO Shortlist 2015, problem N1. So yeah, any questions? Someone asked me a few minutes ago, how do you get that floor function value? Which part was that in reference to? If you are still wondering, or I don't know which part of the solution that would be specifically referencing.
Please move on.
The floor function is just when you round down, sort of, you can think of it. And so in this case, I'm only just sort of using that when you round down from an integer plus 1/2, 4.5, you could always just round down to 4. And then you just sort of can get this stuff and do various things to it. I don't want to spend that much longer on this. You can find the problem, you can find some old IMO shortlist problems on the IMO website, or you can find discussion on the Art of Problem Solving threads on artofproblemsolving.com. There's good stuff there. I think and if you're confused about the floor function, you might also want to look at its Wikipedia page. I don't want to spend way too long on it. I don't want to spend very long on this because I want to get through a lot of problems. So I guess but basically you can just think of the floor function as rounding down. So yeah, let's move on, I think. So let's move on to this IMO 2009 number 1. Yeah, it is floor function, FLOOR. F-L-O-O-R. And then, like there is also the ceiling function that would round up. So like, floor and ceiling, it's a little bit of a cute name, but it works. Anyway, let's move on, I think, to this IMO 2009 number 1. So this tells us we have a positive integer n, and then we have some distinct, pairwise distinct, so they're all different. Any pair of them is different. Into positive integers a1 through ak for some k that is at most 2. Some k that is at least 2. And we're told that n divides a sub I times a sub I minus I, a sub I plus 1 minus 1 for all I. And so and then the problem is prove that n does not divide a sub n times a sub 1 minus 1. So yeah, let's take a moment to think about this, and then not a sub n, a sub k. So yeah, take a moment to think about this, and then I'll tell you the solution, or one way of doing it. Okay, so yeah, someone suggests, obviously, yes, we definitely want to do a proof by contradiction. So, okay, assume for contradiction, this happens. Assume for contradiction. So we want to get some sort of contradiction out of this. Because now the point is that there would sort of be a cycle. You sort of have a cycle of like A1 and A2, A2 and A3, and then AK goes back to A1. And so we want to prove that this cycle is a problem. And so, yeah, I'll go with this. There is this suggestion in the chat, like when is, looking at the GCDs. There are a couple of ways of doing this problem. So I can show a way that sort of focuses on that. So like, you don't want to handle it too directly, but like, basically, I think this maybe, I can say a few words about this. Yeah, okay. Let's sort of look at n. Let's look at the prime factorization of n. So let's consider it as like p1 to the e1 times pr to the er for some positive integer r. And so like for any prime p, that divides n, then like if it divides it to some power e, let's say like p to the e divides, if this happens. And then for all I, including I plus k, and then we're just going to say like a sub k plus 1 equals a sub 1, so that we can just sort of wrap around. So this happens for all I from 1 to k. And so let's look at it this way. For any I, if a sub I is divisible by p for any I, then we would have a sub I minus 1 times a sub I minus 1. This happens. But the GCD of p to the e and ai minus 1 will be 1. And so we're going to want to repeatedly use this fact that if you have positive integers a, d, and b, such that d divides a times b, and the GCD of b and d is 1, then d divides a. And you can look at this just by like thinking about their prime factorizations again. Like D and B don't have any common prime factors, and then you can just see like, for any prime factor dividing D, the exponent to which it divides AB is the same as the exponent to which it divides A, because B doesn't have any factors of it, and so you can get the conclusion. Because then, you know, the exponent, you can think about that. Anyway, so now we can say, if P divides AI, then it doesn't divide AI minus 1, meaning P to the E and AI minus 1 are relatively prime. AI minus 1. Meaning, by this, that P to the E divides A sub minus 1. But in particular, this means P divides A minus 1. So we can do the same argument, but replacing I with I minus 1, get P to the E divides AI minus 2. And then you get that it divides it, you know, keep going. It divides AI minus 3, it divides AI minus 4, and eventually you get that P to the E divides all of them for all j. This upside down A means for all. So P to the E divides AJ for all j. So in this case of P divides any of the numbers, for any prime P dividing n, if you take P to the E as the power to which it divides, you know, the power, the maximum power dividing n, then if P divides any of the numbers, then P to the E divides all the numbers. Otherwise, what happens if P doesn't divide any of the numbers? Well then, if P doesn't divide AI for any I, then that means the GCD of P and AI is 1. I mean, so this would mean the GCD of P to the E and AI is 1. They wouldn't, you know, they won't have any common prime factors. And so this would mean P to, by the same logic, P to the E would then divide AI minus 1. And then we can do this for every I, because we're assuming that P doesn't divide any of the AIs, so we can apply this logic to each of the I's separately. Like if we're assuming that P doesn't divide any of the I's. And then we would get that P to the E divides, if we, like, I guess it's easier to say, like, turn these into, just to get a handle on AI. And so if P doesn't divide any of the numbers, then P to the E divides any of the number, every of the numbers minus 1. So these are the only two cases. Either P to the E divides every number, or P to the E divides every number minus 1. But that's kind of a problem. Why? Well, basically, there's this result that I didn't talk about yesterday, but that can be useful to think about. And it's known as the Chinese remainder theorem. And so one way to think about this result is that sort of like, if you know, like knowing how a number behaves modulo some other numbers, if those other numbers are all relatively prime to each other, is the same as knowing how it behaves modulo their product. And so, like, basically, intuitively, we know how all of the AJ behave modulo every prime power that goes into n maximally. And they all behave the same for each prime. There might be some primes where it divides them all and other primes where it divides each of them minus 1. But for each prime, it's all the same. And so like we expect them to behave the same modulo. And since their behavior is the same modulo all the prime powers, it should still be the same when we mod them all together. And then they would have to be all congruent modulo n, but we said they're all distinct. That's the contradiction we want to get. And so I've sort of been a bit, you know, I'm sort of not being very rigorous about it. If you wanted to sort of formalize this, then you could just sort of say like, you don't really need to cite the Chinese remainder theorem, at least not for this version of what we want to do. You can just sort of say like, take any s and any t between 1 and k. So now consider these numbers as and at. What is their difference? Either for each prime p dividing n, and the exponent e to which we want to raise it, either p to the e divides both as and at, in which case it divides their difference, or p to the e divides as minus 1 and at minus 1, in which case it divides their difference, which is again this as minus at. So in any case, this number divides as minus at. And now we can use this fact that like, if a bunch of numbers divide a number, like, or one way to look at it is just like, now as minus at must be divisible by the least common multiple of all of these different prime powers. And that'll just be n. Like, you know, each of the exponents must be at least what it is in n. And so we get, by just combining them all together for all the different primes, and we would get n divides as minus at. But, you know, just if you just pick your favorite two indices, even if you just picked 1 and 2, because we assumed k is greater than 2, greater than or equal to 2. So if you just pick 1 and 2, then like, you would get n divides a1 minus a2. And this is just a contradiction, because a1 and a2 would be distinct numbers between 1 and n. And so they can't be congruent modulo n. And so this is the contradiction that we wanted. And so this solves the problem. And this is sort of the general idea that like, if you have some numbers like d1 through dr, or I guess d1 through dx, all divide a number m, and they're all pairwise relatively prime, the GCD of any two of them is 1, then their product must divide the number. And again, you can just think of this by looking at the prime factorizations. And so yeah, this gives the contradiction that we needed, meaning our assumption that n divides ak times ai minus our assumption that n divides ak times ai minus 1 is false, meaning we must have n does not divide ak times ai minus 1 as desired. We're done. An alternative way you could have done this problem that would be sort of, maybe you could have done it in a slick, you could have done it in a slicker way by saying like, just again, assume for contradiction, and then if you just look modulo n, then you would have ai times ai minus 1 would be congruent to ai modulo n. And now like, if you just take all the numbers and just sort of multiply them all up, starting from I, and then just like wrapping around, when you hit from k go back to 1, then you can sort of collapse it. Like if you had a1, 2, 3, 4, you could say this is congruent to a1, 2, 3 because of the a3 and a4, congruent to a1, a2, congruent to a1 modulo n. But then like you could do this from any point. You could have started at 2 and then like collapse the 4 and the 1, the 3 and the 4, the 2 and the 3. And then you would just get any of the numbers is congruent modulo n to the product of all of them. And then you could get a similar contradiction looking modulo n. So that's an alternative way you could have done it. But yeah, there are multiple ways. There's more than one way to do this problem. So yeah, that's IMO 2009 problem 1. Any questions, or should I move on?
I think that another solution will be n is equal to pq, such that p divide a1 and q divide a2 minus 1. And we suppose that n divides ak multiply a1 minus 1. Yes.
Right. So in that case, basically, like, like the point is that we're sort of looking at every prime number separately. So like, if we did have this p dividing a1, like you said, like we're sort of, for each prime factor of n, we sort of break into two cases of it divides at least one of the numbers, in which case you do this logic to get this, like p divides ai implies p to the e divides ai minus 1 by looking at this expression, because you don't get any factors of p in here. And then you would just sort of use this to get that p to the e divides all the numbers in the case when p divides any of them. So the one case is p divides any of the numbers, and the other case is it doesn't divide any of the numbers, in which case we did some reasoning, maybe I erased it, to get that, like, oh, this reasoning, you get that p to the e divides any of the numbers minus each of the numbers minus 1. And so those are the only two cases of, like, for each prime power, either it divides all the numbers in the one case, or it divides all the numbers minus 1 in the other case. You know. And so and then you use that to sort of combine the numbers like this by looking at the cases of, you know, maybe, oh, I guess you know. And then, so, yeah. So, I hope, is that clear, I guess? Should I move on? So, okay, if there are no other questions about this problem, I guess I'll sort of, and I know this would go over time, but I hope, would it be okay to do, like, would people be okay with seeing like one other problem, or maybe two, or maybe more, like, if so, like, what do people want to see? Because I think maybe I should, I think I want to show this IO shortlist 2013 N1. So I hope it's fine if I go a little bit over time. I hope it was fine. Like it seemed okay when I did it yesterday, so I hope it's fine to go somewhat over time.
You can continue.
Again. Okay, good. Yeah. So let's move on to this IMO shortlist 2013 N1. And so this is sort of an example of a type of problem, you know, a functional equation in its broadest sense. Basically, so yeah, it's a functional equation. And you would more often see this type of problem in algebra. For example, the IMO of 2015, of 2017, and of 2019 all featured functional equations that were algebra problems. But, you know, occasionally a problem like a number theoretic functional equation will show up, like on the IMO in, I think it was 2010, there was a number theoretic functional equation. And so, you know, occasionally such a problem maybe will show up on some contest. And so since functional equations are a pretty, you know, popular topic, it's good to know like what to do with one when you see one. And so whether it's a number theoretic one or an algebra one or whatnot. And so this problem asks, when n is, so okay, n is the set of all positive integers. This is just sort of a fancy letter n. Positive integers, and then the problem asks, find all functions f from n to n such that for positive integers m and n. We have that, let me double check. We have that m squared plus f of n divides m f of m plus n. And so this is sort of like what you think of a functional equation. Like there's some expression and you have to sort of use it. And so if you've never seen a functional equation before, you might not really know what to do with it. And so like there are some things to be careful of. You can't really assume that f has any sort of nice properties. You don't get to assume that it's a polynomial or something. All you know is that for each integer, it assigns some other integer. It assigns some integer. And then you have to sort of use these conditions to sort of you can somehow work with it for a value of n, values of m and n, or different pairs of m and n, and somehow use it to give you some useful information. And so first of all, what's an obvious function that satisfies this? Or like what's sort of an easy example of a function?
F of n equals n, or f of x equals x.
Yes. So f of x equals x for all positive integers x. For all positive integers x. Yes, it will work because it'll just tell you m squared plus n divides m squared plus n will turn into what we want. And yeah, of course, that's true. So this is a function that works. And on an Olympiad, like, you do want to be careful to like explicitly say like this is a function and it works, and you might want to even like sort of check why it works, because like if you were to solve the problem except you don't like check that the answer actually works, you will lose a point. There are several instances of people losing a single point on a functional equation if they don't check that the function actually works. So you be careful about that. You wouldn't want to like get a 6 instead of a 7 or something. And so yeah. So now how can we show that this is the only function that works? Because it turns out it is. So okay, take some function f that works. Now what can we do to just what do we get when we just plug stuff in? So there are several things we could do. One way of solving it that I can show you is like, for example, what if we plug in m and n are the same number, say k? There are several ways you could do this, but here's one. If you plug in there the same number, you get this. And now if we think of, the Euclidean algorithm again to get rid of this f of k, you get this, and so k squared plus f of k divides k cubed minus k. And now notice something about this. This might give you some information in certain small cases, or one in particular. Specifically, if you take k as 2, equivalently, if you plug in m and n equals 2 into the original problem, this eventually will give you 4 plus f of 2 divides 6. Okay, but because getting k is 2 here. So or you could have just plugged in 2 directly and so get this either way. But now look, this is at least f of 2 is a positive integer. So the only divisor of 6 that's greater than 4 is 6 itself. So 4 plus f of 2 is 6. So f of 2 is 2. And now look, we have a value that we know what to do with. Let's work with it. So hang on. If you
you
Oh, yeah.
again repeat that process of like k cube 1 on the right hand side?
Oh, yeah. When you plug in k and k for any positive integer k, you get k squared plus f of k divides k times f of k plus k. So you get this. But then also just multiplying this by k, you get k times f of k plus k cubed is divisible by this. And so when you subtract them, you get k squared plus f of k divides k cubed minus k. This is sort of thinking about the Euclidean algorithm to sort of get rid of this f of k. And then if you plug in k equals 2 into this, you get 4 plus f of 2 divides 6. And then the only divisors of 6 are 1, 2, 3, and 6. But since f of 2 is a positive integer, the only option that would work here, because this is greater than 4, would be 6 itself. Because 1, 2, and 3, those don't work. It has to be at least 4, so it would be 6. And so 4 plus f of 2 equals 6, so f of 2 equals 2. And so this is only one value, but it'll turn out this will give us the foothold, sort of, that we need to sort of figure out everything else. Because now that we have a value, we can plug it in for one value, or we can plug it in for the other value. So if you take some positive, just for any positive integer k, instead of plugging in k and k, if we plug in k and 2, we get k squared plus f of 2, and we know f of 2 is 2, so just k squared plus 2 divides k times f of k plus 2. Also, if instead of plugging in k and 2, if we plug in 2 and k, we get 4 plus f of k divides 2 times f of 2, 4, plus k. And now, this just gives us what we want, because we don't even have to do any big fancy number theory. All we have to do is just say that any divisor of a positive integer is at most the integer. So we can just say k squared plus 2, because this k squared plus 2 is less than or equal to k f of k plus 2. We'll give you f of k is at least k. Just, cancel off the 2's, divide by k, because it's a positive integer, and you get this. But this gives 4 plus f of k is less than or equal to 4 plus k. Subtract the 4's, you get f of k is less than or equal to k for any k. And now just this gives us f of k equals k for any k. So we're done. We showed that f of k equals k for all k is a solution, and we now show that any solution has to be that, so that's the only solution. So we showed this problem. And so we're done. Any questions about this?
Can you please again repeat that k after that you found out f2 is equals to f2, then you put the value. It was only in the case of m is equals to n, right? So
Well, the point is that when we have this functional equation, you can plug in anything you want. Maybe it would help if I used a different variable. So, or basically here we said, okay, for any k, for any k, you know this. And so you know this, and then we do this. Also for any k, we know this. It might help to there's sort of a notational thing you can use where you sort of, never mind. Also for any k, we know this. And for any k, we know this. So you can plug in k and k. You can plug in k and 2. You can plug in 2 and k. And so plugging in a bunch of different stuff. Or and maybe it would be easier. If you were actually writing it up, you wouldn't have to bother with this generality. You could just say plug in 2 and 2. Then 4 plus f of 2 divides 2f of 2 plus 2. And 4 plus f of 2 divides 2f of 2 plus 8. Then 4 plus f of 2 divides 6, blah, blah, blah. Then for any positive integer k, we know this by plugging in 2 and k. By plugging in k and 2. We know this by plugging in 2 and k. And then do this stuff to get as before. The point is you can plug in anything. And so it can be useful to plug in a bunch of stuff to get it to work together. These solutions to functional equations, this is a pretty, fairly short solution maybe. There can be, when you solve a functional equation, there can be a lot of like plugging various things in to like say, oh, plug in this and that, plug in that and this, and all sorts of stuff. They can be pretty difficult problems. And this isn't the only way of doing this problem, of course. There are other ways of doing it. But this is one way. So yeah, any other questions about this problem?
That when you put like 2k values like m is equals to 2 and n is equals to k, then 4 cancel out, right? Then where does the inequality like f of k is like smaller, might be smaller than k also, no?
Oh, so basically what we're just doing is, I'm just using some very simple inequalities that like any divisor of a positive integer is at most that integer. Like if d divides, you know, d prime, then d is at most d prime. And so here I'm saying, we know this, for any k we know this, so we know this. And we get this. So this must hold for any k. Also, for any k, we know this, 4 plus f of k divides 4 plus k. So we know this 4 plus f of k is at most 4 plus k. And so we know this for any k. So we know f of k is greater than or equal to k for any k. And f of k is less than or equal to k for any k. So f of k equals k for any k, just by combining the for any k. So yeah, any other questions about this problem, or should I move on and do maybe one more problem? We could see this. If I were to do one other problem, which one do people want to see of the ones I haven't done so far? Anyone have any preferences of which one we do?
Perfect problem.
The which one?
The problem involving perfect square.
Okay, yeah, I think someone messaged me about that problem. Here, let's do this. I think we'll do this perfect square problem, and then maybe that'll be the last one I showed today. Someone else wanted to see this. Well, here, let's show this problem, and then that'll probably be the last problem. So, okay, basically we wanted to find all n, all positive integers n, to make 2011 to the n plus 12 to the n plus 2 to the n a perfect square. And so someone, you know, messaged me saying n plus 1, n equals 1. And yes, that is the answer. So yeah, it is n equals 1 and only n equals 1. And so like if you just plug in n equals 1, you get 2011 plus 12 plus 2, which is 2025, which is 45 squared. So yeah, that works. And again, you would want to be careful to like say n equals 1 is the answer. We can see n equals 1 works by doing this. And then for any other n, you can use this sort of idea of looking at moduli. Basically, if n is greater than 1 and odd, then if we look modulo 4, 2011 to the n would be like 3 to the n, and like it'll alternate 3, 1, 3, 1, 3, 1. And so this will be 3 mod 4 when n is odd. 12 to the n, well 12 is, you know, 12 is divisible by 4, this will be 0 mod 4. And then 2 to the n, when n is greater than 1, it's divisible by 4, so that'll be 0 mod 4 for n greater than 1. And so when we add all these up for n greater than 1 being odd, you would get that this is 3 mod 4. And then like if you just look at all the perfect squares mod 4, just 0 squared, 1 squared, 2 squared, 3 squared, which are the only, wait, am I writing in the, oh, okay. Like, then the only, any perfect square is congruent to one of those mod 4, and so the only options for perfect squares mod 4 are 0 and 1 mod 4, and so it can't be 3 mod 4. So any greater than 1 and odd fails. And so like we could have looked at this as just sort of like trying to figure out like, oh, when, like we could have just looked at it as sort of like, we'll take this mod 4, when does it fail? And then we could have said, okay, for n is greater than, if we're trying to solve this problem, we might want to just say, oh, look at it at mod 4, what does that tell us? And so you would have said, okay, that doesn't solve the problem immediately, but it tells me something about which n can or can't work. And so, but you could have seen that when n is even, this would give you 1 plus 0 mod 4. And so that wouldn't give you a contradiction. You wouldn't need to mention that if you were actually writing it up. But if you were trying to solve this problem, you would probably want to look at like all the cases and see which cases do or don't work for looking at it mod 4. And so, okay, we know that n equals 1 works and any odd number greater than 1 fails. So we're only left with the even case. And so, okay, mod 4 was a good modulo. What about mod 3? Well, if n is so just focusing on the even case, if n is even, looking at it mod 3, 2011 to the n. Actually, I guess we can just, well, we don't need to, you could look at it in terms of Fermat's little theorem, but you don't need to do that here. Just say like 2011 to the n, or just let n equal 2k, say. 2011 to the 2k, 2011 is congruent to 1 mod 3, so this is 1 mod 3. 12 is divisible by 3, so again, this will just be 0 mod 3. And then 2 to the 2k, 4 to the k, congruent to 1 mod k, 1 to the k, because 4 is congruent to 1 mod 3, so that's 1 mod 3. And so this number would be 2 mod 3 in the sum. But no perfect square can be 2 mod 3. Because if any perfect square would be 0, is congruent to 0 squared, 1 squared, or 2 squared mod 3, which gives you 0, 1, and 1 mod 3. So we get a contradiction modulo 3 in the even case. And now we're done. N equals 1 works. When n is greater than 1 and odd, it fails for modulo 4 reasons. When n is even, it fails for modulo 3 reasons. So n equals 1 works, and it's the only number that works, so we're done. And another way you could have done this n is even case is by using, instead of looking at moduli, you could have looked at size, how large the numbers are, like where this number is. You could have looked at some inequalities, because this number 2011 to the 2k plus 12 to the 2k plus 2 to the 2k, it's the square. If it were to be a square, it's greater than 2011 to the k squared. But if you look at, so it can't be, if it's a perfect square, since it's greater than 1 perfect square, it would have to be at least the next perfect square. But what is this next perfect square? 2011 to the k plus 1 squared. Well, that's 2011 to the 2k plus 2 times 2011 to the k plus 1. But over here, we would have 2011 to the 2k plus 12 to the 2k, that's just 144 to the k, plus 2 to the 2k is 4 to the k. And so clearly this is greater than this. So we would have, because 144 to the k is less than 2011 to the k, 4 to the k is less than 2011 to the k, and then you can just write a clear inequality. You don't even need the plus 1 over here. But that just is sort of extra, like icing on the cake or whatever, like it's just extra that makes it even bigger. And so this number would be between 2 consecutive perfect squares, so it can't be a perfect square. So that's an alternative way you could have done this problem. So that's, so anyone have any questions about this problem? Well, I guess I could show one more problem. If someone someone asked to see the problem from the UCMO problem, I guess I could show that problem. So I guess I can show that one without taking too long. And then maybe that'll be the last problem. Okay, and so we're asked what positive integers can be written in this form for some positive integers x, y, and z as least common multiple x, y plus least common multiple of y, z divided by the least common multiple of x and z for some positive integers x, y, and z. And so first of all, like if we just play around with some examples, for example, if you have 1, 1, and 1, you notice 2 works. And like if you just play around with some examples, you might notice like if you just take x and z to be 1, you get y plus y divided by 1, 2y. So any even number works. And so, you know, you could just say for any k, plugging in x is 1, y is k, z is 1, gives you 2k, so any even number works. And those are the only ones that work. There are more complicated ways to make any even number work, but that is a way that works. So just, so yeah, any even number works. And so that turns out to be the answer. So to complete the proof, once you tell how any even number works, you would need to say, why does an odd number fail? So let's say we had, so assume for the sake of contradiction, we had some odd number t that worked. So let's write it as LCM xy. We can say this. And so, basically, since t, it's going to help us to look at powers of 2. Yeah. So let's rewrite this in this form. LCM xy plus LCM yz plus negative t times LCM of x and z is 0. So, you know, you can do some casework on the powers of 2 that divide the numbers, but I want to sort of minimize the amount of casework I have to do. So let's write it in this form, and then let's say, okay, so let's consider the maximum power of 2 dividing x. Let's say 2 to the a, or no, like, let's consider the power of 2, the maximum power to which 2 divides x, some non-negative integer. And like a standard notation for this could be like v sub 2 of x. And similarly, you could take v sub 2 of y and v sub 2 of z. So, you know, maybe if x were 120, this would be 3, because 2 to the 3 divides 120, but 2 to the 4 doesn't. And so in some order, we can take these to be some numbers a, b, and c, with a greater than or equal to b greater than or equal to c in some order. And so whenever you have the least common multiple of 2 numbers, you have that the greatest power of any prime dividing that least common multiple is the maximum of the least common multiple of like the powers dividing it. So like, you know, you could say like v sub p of LCM of m and n is the maximum of v sub p of m, v sub p of m. And again, this is just one of those sort of look at the time factorization things. So in some order, the maximum exponents of 2 for LCM of xy, LCM of yz, and LCM of xz are the maxima of these in pairs. So in some order, it would be max AB, max BC, max AC. So A is greater than or equal to B, so the max of A and B is A. A is greater than or equal to C, so the max of A and C is A. B is greater than or equal to C, so the max of B and C is B. So these are the maximum powers of 2 dividing the 3 LCMs in pairs. And so if T is, and so we can consider the maximum power of 2 dividing any non-zero integer. It doesn't have to be positive. As long as it could be positive or negative, as long as it's not 0. And so, you know, this is a negative integer, but it's not 0. So we can consider its maximum power of 2. And in fact, you know, since T is odd, we assumed T is odd, the maximum power of 2 dividing this LCM, this number, is the same as just the max, and the negative doesn't affect anything. So the maximum power of 2 dividing this is the same as the maximum power of 2 dividing LCM xz, whatever that is. Meaning the v sub 2's of this number, and this number, which, as we said, they're all non-zero, so they're all well-defined, are these in some order. But now we're going to get a contradiction out of this. Because now we can rearrange them to fit these numbers in some order. So reordering the terms if necessary, let's write this equation as u plus v plus w equals 0, where the maximum power of 2 dividing u is a. The maximum power of 2 dividing v is a, and the maximum power of 2 dividing b is w. I mean, sorry, the maximum power of 2 dividing w is b. I mean, like 2 to the b, you know, the same exponent deal. Okay, and so now we're going to use one of the features that makes 2, you know, 2 sort of a special number. We're going to use some special property that 2 has. Because, like, actually, I can just sort of put it this way. Let's rewrite this as like u plus v equals negative w. And so 2 to the a divides v. I mean, 2 to the a divides u and v. So it divides negative w. So we can say u over 2 to the a is an odd integer. V over 2 to the a is an odd integer. So now this negative w over 2 to the a, it must be an odd integer plus an odd integer, which must be even. But that's going to give you a problem, because this, like, if we ignore getting rid of the negative, this w over 2 to the a is an even integer. So we can divide by 2 again to get that w over 2 to the a plus 1 is an even integer. I mean, sorry, not an even integer, it's an integer. Meaning the maximum, so yeah, w over 2 to the a plus 1 is an integer. So the maximum power of 2 dividing into w is at least a plus 1. But it's b, we assumed it's b. So a plus 1 is less than or equal to b. But we said a is greater than or equal to b. So we would have this and this. This is a contradiction. So our original assumption that this odd number worked fails. So we're done. Odd numbers fail, and we said earlier how even numbers work, so this solves the problem. Are there any questions about that? That was a little bit complicated, I know.
So are we gonna conclude this here now?
I guess maybe this, yeah, I guess I've already gone a while over time, so maybe we'll leave that there. And so, yeah, and someone asked me if I had any like sort of daily math Olympiad class. Not exactly, but there was a thing last summer that I did called Math Divulged. You should be able to find it just by Googling. Let me, if you just go to, let me write that down. I can put the link in the chat.